Hi, Intro to Calc. How you doing? Hope you're having a great day. We are starting. Um, this is the first kind of lesson that's new for us. So this section is about continuity of functions. So we're going to talk about what it means for a function to be continuous, and we're going to talk about something called the Intermediate Value Theorem. Which in words sounds kind of challenging, but it's really not that hard if you think about like what it actually means on a graph. So first thing we're going to talk about is continuity. So a function is determined to be continuous if you can essentially, this is like not special, like this is not official math terms, but like you can tell if a function's continuous if you can draw it without picking up your pencil or pen. Okay, so basically a function's continuous if it has no jumps, skips, asymptotes, etc. And basically in layman's terms it means that you can draw it without picking up your pen. So we're going to look at two examples before we go on to the next definition, but we're going to look at these three different functions. So we have figure 1.79, which is a graph of 3x cubed minus x squared plus 2x minus 1. And this graph, like if you look at it, I can trace it without ever picking up my pen, which would give us an indication that it's continuous. The idea here is that maybe we don't necessarily know what's happening like in the long run, right? And usually there are arrows to indicate like it just keeps going down on that side or it keeps going up on that side. But if we don't have that information, it may be discontinuous somewhere else. But for now, what we know is that on the interval that we have, right, in the area that is given, we know that this function is continuous. You can also tell from the equation of the function, 3x cubed minus x squared plus 2x minus 1. If there are no like even roots, which would have problems at negative numbers, there's no variables in denominators, in which case you'd have problems when the denominator is 0. Things like that will be an indication also of discontinuities. So this one is just a polynomial, and you'll be able to plug in any value for x. Your domain is negative infinity to infinity, and your range is negative infinity to infinity as well, all real numbers for both domain and range, which is, so you should be able to then generalize and say that the whole function is continuous. This next example, f of x equals 1 over x, if you look at the actual equation, 1 over x, you know that there's going to be a problem when x equals 0 because you'll be doing 1 divided by 0. And if you ask anybody, Siri included, what happens when you divide by 0? Bad things happen. Don't divide by 0. So you can't have this happen because things blow up and it's bad news. So can't divide by 0. So that is your algebraic argument that like there's going to be a discontinuity at x equals 0, but you don't know for sure, but you can look at the graph, right? So if I'm looking at the graph and I'm drawing I get down here, right, and this does continue all the way down to negative infinity, but it never quite reaches the y-axis here. So in order to draw the whole thing, I would have to pick up my pen and then jump to the other side and then keep drawing. So that would be discontinuous at x equals 0. Now if we're looking at a different interval, maybe we're looking from negative 1 to negative 1/2 or something, you might have continuous function just in that range of values within that restricted domain. But overall the function is not continuous. And this last one is an example of a step function, and the cost of mailing a letter would be, the example. So it costs $0 to send 0 letters, but as soon as you, or not 0 letters, this is the ounces of the letters, how much they weigh. But as soon as you are sending something that weighs more than 0 ounces, you jump up to 45 cents. And then as soon as you hit 1 ounce, you are still paying 45 cents, but as soon as you go over 1 ounce, so 1.00001 ounces, you have to jump up to the next pay amount, the next, the next level, the next bracket. So you're paying 65 cents for anything between 1 and 2 ounces. So obviously this is going to be discontinuous because I can't draw it without picking up my pencil and moving to the next section of the graph. So these two are discontinuous, this one is continuous. So one of the reasons continuity is important is because sometimes if we don't know what's happening with a function, but we know that it's continuous, we can make some conclusions about the graph or the function itself. So for example, on f of x, if I only knew that the function went through the point -1, -5, I know it goes through that point, and I also know it goes through the point 1, whatever this is, 1, 4, let's pretend. I'm just making these up, okay? Let's pretend we only knew that it went through those 2 points, okay? If we also know that it's continuous, then we know that somewhere between -1 and +1, so somewhere between here and here, we know there has to be a 0 because there are no jumps and skips. So if I go from a negative number, mainly -5, and I don't know what happens, but in order for me to be able to get to the next spot, I have to cross the x-axis at least once, okay? Not necessarily exactly once, but I know it has to happen at least once, and that's actually quite important. Also, this is not a function because it doesn't pass the vertical line test, the thing that I drew, but I'm just trying to make a point, okay? So if you know something's continuous and you know it goes from a negative y value to a positive y value on an interval, you know that it has to cross the x-axis at least once. It could also go through twice or 3 times, like that, right? But we know it has to cross the x-axis, which is important. You only know that if we know that it's continuous. And that leads us to the intermediate value theorem, because basically what the intermediate value theorem says is that if I have an interval from, like, let's say A to B, okay, let's call it, we have the interval on the x-axis, here's A, and here's B, okay? So, and this function is f of x. So we're going to call whatever this y value is, right? It's just some y value. And we get that by plugging a into f of x. So this is f of a. And then that means that this up here, what is the y value that goes along with b. And so that I'm going to call f of b because it's the same thing as plugging b into f of x. Okay? Basically, what the intermediate value theorem says is that if there is a y value that occurs between f of a and f of b, so like here, there's some number here. We're just going to call that k for now, just because I can. Okay? So if there's a number k in between f of a and f of b on the y-axis here, then there has to be an x value here that gets me that k value. So we're going to call this c. So we know that there has to be some c so that f of c equals k. Okay? Basically, all that means is if this number is 1 and this number is 5, there's a number between 1 and 5, like 3 or 4, for example, let's call it 3, there has to be some value of x that corresponds to that to get me 3 as a y value. And that's all the intermediate values theorem says. And here's the fancy way of saying it. This is only true for continuous functions, right? Because if it's not continuous, then you could have a value, like a y value at 45, and another y value at 65, but there may not be a number that in between those two values that would get you a y value of 55 or 50. So this is only true for continuous functions. So we say if f of x is continuous on an interval a to b, right, this is your x interval, then for any number k between f of a and f of b, so that's a number in between the y values, there must exist at least one number c in the interval a to b, so one x value between a and b, so that when you plug that value into the function, you get out k. Okay, basically, it has to exist, right? You can't just skip a number. In between 1 and 5, you can't skip 3 because 3 is in between 1 and 5. And unless you are literally picking up your pencil and plotting something, you can't skip a number in between 1 and 5. So that's all the intermediate value theorem says. I know it sounds like kind of confuzzled and it has a lot going on in it, but that's basically what it says. You can't skip numbers as long as you have a continuous function. You can't skip y values, and so there has to be an x value that gives you that y value. Okay, so continuity of a function at a specific point is, roughly speaking, it just means that like nearby x values to x1 give nearby values of the y value. So, for example, like at this graph, right, a nearby x value of 1 might be 0.99 ounces, and that would give me a y value of 45 cents, right? And if I go to another nearby value of 1, which is maybe 1.01, right, a really close value to 1, I get a y value that is not near 45, it's 65, right? I would go up here, and I'm at 65 cents. 45 and 65 are not close when you look at how close the x and the y values are. And so that's like a good indication that you skipped a number, you jumped, and therefore the function is discontinuous at that point, okay? So we're going to try a couple examples. So here are the examples for you. And it might be a good idea to pause the video right now and go ahead and try each of these problems. And then I'll go through the answers in the next 2 minutes, and hopefully you'll kind of get the hang of it. Okay, so for A, you can see, if you were to graph it, you could see it's discontinuous. There's an asymptote, a vertical asymptote at x equals -3, because it makes the denominator 0. And since -3 is in between -5 and 0, which is like the interval we're looking at, we know it's discontinuous on that interval. And if you wanted to, you can kind of look at that table. So I just plugged in numbers that are close to -3, so -2.9, -2.99, -3.01, -3.1, and I find that the numbers jump drastically large amounts. So it's from 10 to 100 to a -100 to -10, which is a good indication that it's discontinuous as well. E to the x on 0 to 1 is e to the x is a continuous function, so it will be continuous everywhere, but here's that interval 0 to 1. This problem was actually poorly designed. It's actually not possible to do unless you have a y-intercept here. So if you can figure out a way to do that, come into class and like we can discuss it. But this is a piecewise function, so if you need to refresh piecewise functions, that's something to come in about or ask in class, okay? And then this last one is just sketching a continuous function, so you literally can just kind of like connect the dots, And that's it. Okay, cool. Good deal. Bye.